What if I told you that right now, at this very moment, you're being pulled by every single object in the universe? The coffee cup on your desk, the phone in your hand, the planet Jupiter 365 million miles away, and even galaxies so distant their light has been traveling for billions of years just to reach you. You're pulling on them too. But here's what will absolutely blow your mind. Despite gravity being the force you've experienced every single second of your entire life, despite it being the first force you felt when you took your first breath, scientists still have no idea what it actually is. And the quest to control it, to master this mysterious force, might be the most important scientific pursuit in human history. Because here's the shocking truth that most people never realize. We already are controlling gravity. Every time you jump, every time you pick up a pencil, you're temporarily overcoming the gravitational pull of an entire planet. The real question isn't whether we can control gravity. The question is, how far can we push that control? And the answer to that question will determine whether humanity remains trapped on this pale blue dot forever, or becomes a truly spacefaring civilization capable of reaching the stars. Now, before we dive deep into this rabbit hole, I need you to do something for me. If you're already feeling that tingle of curiosity, that sense that you're about to learn something that will fundamentally change how you see the world, hit that like button right now. Subscribe to this channel because over the next 3.5 hours, I'm going to take you on a journey through some of the most mind-bending concepts in all of science. And drop a comment telling me where you're watching from and what time it is there. I want to know if you're watching this during your morning coffee in Tokyo, your lunch break in London, or late at night in Los Angeles. Because gravity, this force we're about to explore, doesn't care what time it is or where you are. It's working on you right now, pulling you, shaping you, defining the very structure of your existence. Let's start with something that seems simple but isn't. What is gravity? You've probably been told it's the force that pulls things down, right? But that's not quite accurate. Gravity doesn't pull things down. There is no down in space. Right now, someone in Australia is experiencing down as the exact opposite direction of what you're experiencing. So what's really happening? Here's where things get weird. According to Isaac Newton, who revolutionized our understanding of gravity in 1687, gravity is an invisible force that attracts any two objects with mass toward each other. The strength of this attraction depends on two things: how much mass the objects have and how far apart they are. This is described by his universal law of gravitation, and the equation is beautifully simple. F equals g times m1 times square meter divided by r squared. Newton figured this out by watching an apple fall, or so the legend goes. But what he actually did was far more impressive. He realized that the same force pulling the apple down was the force keeping the moon in orbit around Earth. Think about how revolutionary that idea was. For thousands of years, humans thought the heavens operated by completely different rules than Earth. Newton showed that it was all connected, all governed by the same mathematical principles. But here's what Newton himself admitted he couldn't explain. How does gravity actually work? How does the Earth know to pull on you? How does the sun know to pull on planets millions of miles away? Newton famously wrote, "I frame no hypothesis about the mechanism of gravity." He could describe what it does, predict its effects with stunning accuracy, but he had no idea how it actually worked. It was just there, an invisible force reaching through empty space instantaneously. And that bothered him for his entire life. For more than 200 years, this bothered scientists. Because instantaneous action at a distance, this idea that objects could affect each other without touching and without any delay, seemed almost magical. It violated a fundamental intuition about how the universe should work. Then, in 1915, a patent clerk turned physicist named Albert Einstein published a paper that didn't just solve this problem. It completely revolutionized our understanding of reality itself. Einstein's general theory of relativity proposed something so strange, so counterintuitive, that even today it's hard to wrap your mind around. He said, there is no force of gravity. The sensation you feel right now, that feeling of being pulled downward, isn't a force at all. Instead, mass warps spacetime itself, and objects simply follow the curves in spacetime created by that mass. Imagine spacetime as a stretched rubber sheet. Now place a bowling ball in the center. The ball creates a depression, a curve in the sheet. If you roll a marble near this depression, it will curve toward the bowling ball, not because the ball is pulling it, but because the sheet itself is curved. The marble is just following the straightest possible path through curved space, what we call a geodesic. This is what gravity actually is. You're not being pulled down right now. You're trying to follow a straight line through spacetime, but Earth's mass has curved spacetime around it, and that curve is what you experience as the force of gravity. Your chair is pushing up on you, preventing you from following your natural geodesic, which would take you toward Earth's center. Here's what will blow your mind about this. Einstein's theory makes a prediction that Newton's theory doesn't. It says that gravity shouldn't be instantaneous. It should travel at the speed of light. If the sun suddenly vanished, Newton's theory says Earth would immediately fly off in a straight line. Einstein's theory says we'd keep orbiting for about 8 minutes, the time it takes light to travel from the sun to Earth, because it would take that long for the change in spacetime curvature to reach us. And in 2015, exactly 100 years after Einstein published his theory, scientists detected gravitational waves for the first time using the LIGO detector. They recorded ripples in spacetime itself, created by two black holes colliding 1.3 billion light-years away. And these ripples traveled through space at exactly the speed of light, just as Einstein predicted. This discovery won a Nobel Prize in 2017, awarded to Rainer Weiss, Barry Barish, and Kip Thorne. It was the final confirmation that Einstein was right. Gravity isn't a force. It's geometry. But if gravity is just the curvature of spacetime, then controlling gravity means controlling the shape of spacetime itself. And that's where things get really interesting. Because unlike electromagnetic forces, which we can shield against and manipulate relatively easily, gravity seems fundamentally different. There's no such thing as anti-gravity shielding. You can't block gravity. Lead, which blocks radiation, doesn't block gravity at all. A thin sheet of aluminum blocks electromagnetic waves, but all the aluminum in the world won't stop gravity from passing right through. The only way we know to create a gravitational field is to have mass. And the only way we know to create more gravitational pull is to add more mass or compress existing mass into a smaller space. But here's a question that should make you uncomfortable. Why is gravity so weak? Think about it. When you pick up a paperclip with a small magnet, that tiny magnet is overcoming the gravitational pull of the entire Earth. The electromagnetic force is vastly stronger than gravity, roughly 10 to the power of 36 times stronger. That's a 1 followed by 36 zeros. So why is gravity so incredibly weak compared to the other fundamental forces? This is called the hierarchy problem, and it's one of the deepest mysteries in physics. Some physicists, like Lisa Randall at Harvard, have proposed a stunning solution. What if gravity isn't actually weak? What if it's just as strong as the other forces, but most of its strength is leaking into other dimensions that we can't see? According to some versions of string theory, our universe might have as many as 11 dimensions, but we only experience 4, 3 of space and 1 of time. The other dimensions might be curled up so small we can't detect them, or they might be vast, but accessible only to gravity. In this model, gravity appears weak because it's diluted across dimensions we can't perceive. But if that's true, then at very small scales, or under extreme conditions, we might be able to access those extra dimensions and tap into gravity's full strength. This isn't science fiction. Experiments at the Large Hadron Collider have been specifically designed to look for evidence of these extra dimensions by watching for mini black holes that would form if gravity becomes strong at small scales. They haven't found them yet, but the search continues. Now let me tell you about the first serious scientific proposal for manipulating gravity and why it doesn't work the way most people think. In the 1960s, during the space race, NASA was funding all kinds of exotic research. One area they investigated was something called gravomagnetism or gravitomagnetism. The idea is based on a fascinating analogy. We know that moving electric charges create magnetic fields. Maxwell's equations of electromagnetism show this beautiful symmetry between electricity and magnetism. So here's the question. If moving mass creates gravitational effects, does rotating mass create something like a magnetic field for gravity? Einstein's equations actually predict this. It's called frame dragging, and it's real. When a massive object rotates, it drags space-time around with it, like how a spoon stirring honey creates swirls in the honey. In 2004, a satellite called Gravity Probe B was launched specifically to measure this effect around Earth. The mission, which took data until 2005 and spent years analyzing results, confirmed that Earth's rotation does indeed drag spacetime around with it, exactly as Einstein predicted. The lead scientist, Francis Everett, spent 47 years of his career on this experiment. But here's the problem with using frame dragging for practical gravity control. The effect is incredibly tiny. Earth, a planet with the mass of 6 times 10 to the power of 24 kilograms, rotating once every 24 hours, creates a frame dragging effect so small that it took one of the most precise experiments ever designed to detect it. The geodetic effect measured was 6.6 arcseconds per year, and the frame dragging effect was just 0.039 arcseconds per year. To create a frame dragging effect strong enough to, say, lift a person off the ground, you'd need something like a neutron star spinning at thousands of times per second. And if you were close enough to a neutron star to feel that effect, the tidal forces would have already torn you into atoms. So gravimagnetism is real, but it's not going to give us flying cars anytime soon. But don't lose hope yet, because there are other approaches that are far more promising. Let's talk about what we're actually doing right now to control gravity, because we are doing it, just not in the way you might think. Every rocket launch is an exercise in gravity manipulation, not by changing space-time curvature, but by using another force, the electromagnetic force, through chemical reactions to overcome gravity. The Saturn V rocket that took astronauts to the moon burned fuel at a rate of 15 tons per second at launch. Think about that. 15 tons every second, all to overcome Earth's gravitational pull. And here's something most people don't realize. You never actually escape gravity. When astronauts are on the International Space Station, they're not in zero gravity. Earth's gravitational pull at the ISS's altitude is still about 90% as strong as it is on the surface. So why do they float? Because they're in free fall. The station is constantly falling toward Earth, but it's also moving sideways so fast that it keeps missing Earth. It falls around the planet. That's what an orbit is, falling and missing. The astronauts are falling too, at the same rate as the station. So relative to the station, they float. They're in free fall, following a geodesic through curved spacetime. But this brings us to a fascinating question. If we can't shield against gravity, and we can't easily manipulate spacetime curvature, what if we could create artificial gravity instead? On a rotating space station, you could simulate gravity through centrifugal force. Stand on the inner rim of a rotating cylinder, and you'd feel pressed outward toward the rim by inertia. This isn't real gravity. It's not curved spacetime, but it would feel identical to someone experiencing it. This is how the space station in 2001, A Space Odyssey, worked, and it's based on solid physics. The concept was actually proposed by Konstantin Tsiolkovsky in 1903 and expanded by Hermann Potocnik in 1929. The question is, how fast would the station need to spin? That depends on its radius. For a station with a radius of 224 meters, you'd need to rotate at about 2 rotations per minute to simulate Earth gravity at the rim. But here's a problem engineers have discovered. If the rotation rate is too high, you get severe Coriolis effects. Drop something, and instead of falling straight down, it curves to the side. Turn your head quickly, and you get disoriented. The inner ear, which governs balance, doesn't like rotating reference frames. Studies suggest that for comfortable living, you want a rotation rate of no more than about 2 RPM, which means you need a station at least 224 meters in radius. That's a huge structure. The ISS, for comparison, is about 109 meters long. Building a rotating habitat of that size in space would require resources and construction techniques we don't yet have, though companies like the Gateway Foundation are seriously planning such structures. But here's what's really interesting. Artificial gravity through rotation isn't just for space stations. If we ever build generation ships to travel to other star systems, trips that might take hundreds or thousands of years, we'll need artificial gravity to keep the passengers healthy. Without it, bones lose density, muscles atrophy, and the cardiovascular system weakens. Astronauts on the ISS lose about 1 to 2% of their bone density per month. On a multi-decade or multi-century journey, that's not sustainable. So in a very real sense, artificial gravity through rotation might be the key technology that allows humanity to become an interstellar species. We may never control gravity in the sense of manipulating space-time curvature, but we can create the effects of gravity, and that might be good enough. Now let me tell you about one of the most controversial topics in gravity research, something that's cost careers and sparked heated debates: the M drive and other supposedly reactionless drives. In 2001, a British engineer named Roger Shah proposed a device called the M drive, which supposedly generated thrust by bouncing microwaves around inside a conical cavity. According to classical physics, this should be impossible. It would violate the conservation of momentum, one of the most fundamental principles in all of physics. A closed system can't generate thrust without expelling something in the opposite direction. That's why rockets need fuel. But Shah claimed his device worked, and in 2016, NASA's EagleWorks lab published a paper suggesting they'd measured a small amount of thrust from a similar device. The physics community went into an uproar. Some were intrigued, most were skeptical, and many were outright hostile. The problem is that the measured thrust was incredibly small, just a few micronewtons, right at the threshold of what could be detected. It could easily be an experimental error, thermal effects, or interactions with Earth's magnetic field. Multiple replication attempts have failed to confirm the effect under rigorous conditions. In 2021, a team at TU Dresden in Germany conducted high-precision tests and concluded that the thrust appeared only when the device was not properly shielded from external effects. When they eliminated all potential sources of error, the thrust disappeared. The scientific consensus now is that the M drive doesn't work. But here's why this matters for our discussion of controlling gravity. The M drive controversy shows how desperate we are to find a way to manipulate gravity or create thrust without reaction mass. Because if we could, everything would change. Interstellar travel would become feasible. We could build ships that accelerate continuously without carrying enormous amounts of fuel. We could potentially create what science fiction calls reactionless drives or even anti-gravity. But physics doesn't care about what we want. It operates by laws that we discover, not laws that we invent. And so far, every single claim of anti-gravity or reactionless drives has either been debunked or remains unconfirmed. That doesn't mean it's impossible. It just means that if it is possible, it will require physics beyond what we currently understand. And that brings us to the cutting edge of theoretical physics. What if I told you that empty space isn't empty? This is going to sound bizarre, but according to quantum field theory, the vacuum of space is seething with virtual particles, constantly popping into and out of existence. These aren't real particles in the classical sense, but they have real effects. One of these effects is called the Casimir effect, discovered by Dutch physicist Hendrik Casimir in 1948. If you place two metal plates very close together in a vacuum, closer than about a micrometer, the plates will be pushed together by a tiny force. This happens because the vacuum between the plates can only support certain wavelengths of virtual particles, but the vacuum outside the plates can support all wavelengths. This creates a pressure difference, and the plates move together. This effect has been measured precisely, and it's exactly as quantum field theory predicts. Now here's where it gets wild. Some physicists have proposed that if we could manipulate the quantum vacuum, we might be able to create negative energy or negative mass. And if we could create negative mass, we could potentially create antigravity. This isn't pseudoscience. This is serious theoretical physics, though it's highly speculative. Miguel Alcubierre, a Mexican theoretical physicist, published a paper in 1994 proposing what's now called the Alcubierre drive. It's a solution to Einstein's field equations that describes a spaceship that could travel faster than light without actually moving faster than light. How? By contracting spacetime in front of the ship and expanding it behind. The ship itself would sit inside a bubble of flat spacetime and could be stationary relative to the space immediately around it, while the bubble moved through space, potentially faster than light. This doesn't violate relativity, because the ship isn't moving through space. Space is moving around the ship. But here's the catch. To create this warped spacetime bubble, you'd need exotic matter with negative energy density. And we have no idea if such matter can exist or how to create it. The Casimir effect shows that we can manipulate vacuum energy, but creating the amount of negative energy needed for an Alcubierre drive would require technology far beyond anything we can imagine. Some calculations suggest you'd need the mass energy equivalent of Jupiter, but made of negative energy. Later refinements by Harold White and NASA suggested you might be able to do it with much less, maybe only the mass of a spacecraft like Voyager 1, but still made of this exotic negative energy that we don't know how to make. So is this impossible? Not necessarily impossible, but it requires physics we don't yet understand. And that's a theme you'll see throughout this exploration. Controlling gravity in the ways we dream about, creating antigravity fields, building warp drives, manipulating spacetime at will. All of these probably require a deeper understanding of physics. They require us to solve one of the biggest problems in modern science, unifying quantum mechanics and general relativity. Because right now, we have two incredibly successful theories that describe the universe. Quantum mechanics describes the very small atoms and subatomic particles with stunning precision. General relativity describes gravity and the very large planets, stars, galaxies, spacetime itself with equal precision. But these two theories are mathematically incompatible. They can't both be completely true in their current forms. At the extreme conditions where both quantum effects and gravitational effects are strong, like inside a black hole or at the moment of the Big Bang, our equations break down. We need a theory of quantum gravity, and we don't have one yet. String theory is one attempt. Loop quantum gravity is another. But we don't yet know which, if any, is correct. Here's why this matters for controlling gravity. Quantum gravity might reveal new aspects of gravity that we can manipulate. It might show us how to create or destroy spacetime curvature in ways we can't currently imagine. It might reveal that gravity is not fundamental, but emergent, arising from something deeper. Erik Verlinde, a Dutch theoretical physicist, has proposed that gravity might be an emergent phenomenon, similar to how temperature emerges from the motion of atoms. If that's true, and we understand what gravity emerges from, we might find ways to control it by manipulating the underlying reality. These ideas are speculative, but they're not crazy. They're serious attempts by brilliant physicists to understand the deepest nature of reality, and understanding that nature is the first step to controlling it. Now we're about an hour into this journey, and I want you to pause and think about what we've covered. We've gone from Newton's force to Einstein's curved spacetime, from frame dragging to artificial gravity, from the M-drive controversy to quantum vacuum energy and warp drives. Each of these represents humanity's attempt to understand and control gravity. And while we haven't achieved true gravity control yet, we've learned something profound. Gravity is stranger and more interesting than we ever imagined. But let's shift gears now and talk about something that affects you personally, something you experience every single day, but probably never think about: how your body has adapted to live in Earth's gravitational field. This is going to change how you see your own body. Every single part of you, from your bones to your blood to your brain, has been shaped by gravity. Your bones are as strong as they are because they need to support your weight against gravity. Remove that weight, send you to space, and your bones start to dissolve. Your osteoclasts, cells that break down bone, don't slow down, but your osteoblasts, cells that build bone, become less active. The result: your skeleton wastes away. Your heart is sized and shaped to pump blood upward against gravity. In space, your heart doesn't need to work as hard, so it weakens. Your cardiovascular system shifts. Blood pools in your upper body and head, and your body responds by reducing blood volume. Astronauts can lose up to 22% of their blood volume in space. Your inner ear, the vestibular system that tells you which way is down, becomes confused in microgravity. About half of astronauts experience space adaptation syndrome, basically space sickness, when they first arrive in orbit. Even your gene expression changes in microgravity. NASA astronaut Scott Kelly spent a year on the ISS, while his identical twin brother Mark stayed on Earth. When Scott returned, scientists compared them and found that 7% of Scott's gene expression hadn't returned to normal even after 6 months back on Earth. Changes in DNA methylation, alterations in telomere length, shifts in gut microbiome composition, all from living without gravity. Your body is fundamentally a gravity-adapted machine. And here's what's truly mind-bending. If we do become a spacefaring civilization, if we colonize Mars or build orbital habitats, we'll be creating environments with different gravitational fields. Mars has only 38% of Earth's gravity. The Moon has only 17%. Children born and raised on Mars would develop differently than Earth children. Their bones might be less dense, their hearts smaller, their muscles weaker. Would they ever be able to come to Earth? Or would Earth's gravity be crushing to them? Like if you tried to live on a planet with 3 times Earth's gravity? We don't know. No one has ever been born in low gravity or microgravity. But if humanity expands beyond Earth, we'll find out. And it's possible that after enough generations, Martians and Earth humans might be physiologically different enough that we'd essentially be different subspecies, all because of gravity. Think about what that means for your own existence. Every breath you take, every step you walk, every heartbeat pumping blood to your brain, all of it is calibrated for exactly 9.8 meters per second squared of gravitational acceleration. You are a gravity organism, shaped by and dependent on this force. And here's something even more personal. Gravity is aging you right now. Not in some metaphorical sense, but literally. The lower part of your body is slightly deeper in Earth's gravitational field than the upper part. And because of gravitational time dilation, a prediction of general relativity, time moves slightly slower for your feet than for your head. The effect is tiny, about 10 to the power of negative 16 seconds per second, but it's real and measurable with atomic clocks. Your feet are younger than your head by about 100 nanoseconds over a 70-year lifetime. Gravity is creating a time gradient across your body. And if you lived on a neutron star, where gravity is billions of times stronger than on Earth, the time dilation would be so extreme that your feet would be noticeably younger than your head, aging at a visibly different rate. Time itself would stretch across the length of your body. Of course, you couldn't actually survive on a neutron star. The tidal forces would tear you apart long before you noticed the time dilation. But the principle stands. Gravity affects time, and that means gravity is affecting your aging process right now. Now let's talk about black holes, because if you want to see gravity control taken to the absolute extreme, black holes are it. A black hole is what you get when you compress mass into such a small space that the curvature of spacetime becomes infinite at the center, creating a singularity. The boundary around this singularity is called the event horizon, and it's the point of no return. Inside the event horizon, spacetime is so warped that all paths lead to the singularity. Even if you pointed a rocket engine away from the singularity and fired it at full thrust, you'd still move toward the singularity, because away doesn't exist inside the event horizon. Every direction is toward the center. This is what it means for spacetime to be curved so extremely that escape is impossible. Not difficult, impossible. Even light can't escape, which is why they're called black holes. Now here's what will blow your mind. We've photographed black holes. In 2019, the Event Horizon Telescope, a global network of radio telescopes working together, captured an image of the supermassive black hole at the center of the galaxy M87. You've probably seen the image. A bright ring of light surrounding a dark circle. That dark circle is the shadow of the black hole, about 38 billion kilometers across, the size of our entire solar system. The bright ring is hot gas orbiting the black hole at a significant fraction of light speed. Katie Bowman, a computer scientist, developed key algorithms that made processing the data possible. The black hole itself has a mass 6.5 billion times the mass of our Sun, compressed into a region smaller than our solar system. The gravitational effects are so extreme that the gas orbiting the black hole is heated to billions of degrees and glows in radio waves. And here's something that sounds like science fiction, but is absolutely real. If you could somehow survive near a black hole's event horizon, time would slow down for you relative to the outside universe. This is extreme gravitational time dilation. In the movie Interstellar, the characters visit a planet orbiting close to a black hole, and 1 hour on the planet equals 7 years back on their ship. The math in that movie was actually calculated by Kip Thorne, the Nobel Prize-winning physicist we mentioned earlier, and it's accurate. That level of time dilation requires being incredibly close to an incredibly massive black hole, but it's possible according to general relativity. If you fell into a black hole, from your perspective, you'd reach the singularity in a finite amount of time. But from the perspective of someone watching you from far away, you'd appear to slow down and freeze at the event horizon, never quite crossing it, because the light from your image would take longer and longer to reach the observer as you approach the horizon. You'd appear to be frozen in time, gradually redshifting and fading away. But here's the really weird part. From your perspective, you could look up and see the entire future history of the universe unfold and fast forward as you fell toward the singularity. Time dilation works both ways. If this doesn't make you feel something, if this doesn't give you a sense of awe at the strangeness of reality, then I don't know what will. Black holes are gravity taken to such an extreme that space and time literally swap roles. Outside the event horizon, you can move freely through space, but are forced to move forward through time. Inside the event horizon, you're forced to move toward the singularity through what was space, and time becomes a direction you can face. The math is clear, but the implications are almost impossible to wrap your mind around. And yet black holes are real. We've detected them, photographed them, measured their properties. There are probably 100 million stellar mass black holes in our galaxy alone, most of them invisible, detectable only by their gravitational effects on nearby matter. And at the center of nearly every large galaxy, including our own Milky Way, there's a supermassive black hole. The black hole at the center of our galaxy, called Sagittarius A*, has a mass about 4 million times the mass of the Sun. We've watched stars orbit around it, and from their orbits, we can calculate the black hole's mass precisely. Andrea Ghez and Reinhard Genzel won the Nobel Prize in 2020 for this work, tracking stars orbiting the galactic center for decades. One star, called S2, completes an orbit every 16 years and gets as close as 17 light hours from the black hole, traveling at up to 3% of the speed of light at its closest approach. The gravitational forces and time dilation effects on that star are measurable. So black holes are the ultimate demonstration of gravity's power. But could we ever use them? Could we harness a black hole's gravitational energy? Theoretically, yes. Roger Penrose proposed in 1969 that you could extract energy from a rotating black hole through what's now called the Penrose process. The idea is that a rotating black hole drags space-time around with it, creating a region called the ergosphere. If you dropped an object into the ergosphere, split it into two pieces, and let one piece fall into the black hole while the other escaped, the escaping piece could have more energy than the original object, with the extra energy coming from the black hole's rotation. This process could theoretically extract up to 29% of a black hole's mass energy, making it the most efficient energy extraction process in the universe. Freeman Dyson speculated that advanced civilizations might build structures around black holes to harness this energy. But we're talking about technology that's centuries or millennia beyond our current capabilities. Still, it shows that even gravity's most extreme manifestation might eventually be harnessed. And that brings us to a crucial point. When we talk about controlling gravity, we need to think on different scales and different time scales. Some forms of gravity control are already possible, like creating artificial gravity through rotation. Others are theoretically possible, but technologically out of reach, like Penrose process energy extraction. And others might require new physics entirely, like creating negative mass for a warp drive. The question isn't just, can we control gravity? But which aspects of gravity can we control, and when? Let me give you a framework for thinking about this, a hierarchy of gravity control technologies from the present to the far future. Level 1, what we can do now. Overcome gravity locally using other forces, like rockets and planes. Create artificial gravity through rotation or acceleration. Level 2, what we might do in the next century. Build large rotating habitats for permanent space settlements. Use gravity assists and orbital mechanics more efficiently for interplanetary travel. Perhaps create small-scale manipulations of space-time using extreme conditions, though this is highly speculative. Level 3, what we might do in the next few centuries if we develop the right technology. Harness the energy of black holes. Create and stabilize wormholes, if they're possible, for rapid travel between distant points in space. Level 4, what would require new physics? Create negative mass or negative energy. Build an Alcubierre-style warp drive. Generate or cancel gravitational fields at will. Shield against gravity. Level 5, what might be possible for a truly advanced civilization? Engineer spacetime itself, creating or removing dimensions. Generate artificial gravity fields without mass. Manipulate the cosmological constant or dark energy. Now, most of our realistic near-term plans fall into levels 1 and 2. And here's what's exciting. Level 1 and 2 technologies, the things we can do now or soon, are enough to establish a permanent human presence throughout the solar system. We don't need anti-gravity or warp drives to colonize Mars or build orbital habitats. We just need bigger rockets, better life support, and rotating structures for artificial gravity. These are engineering challenges, not physics challenges. They're hard, expensive, and dangerous, but they're doable with known physics. But here's where I want to challenge your thinking. Maybe we're asking the wrong question. Instead of, can we control gravity? Maybe we should ask, do we need to? Because gravity isn't just a force that holds us down. It's also the force that holds us together, that created the conditions for life to exist, that structured the entire universe into galaxies and stars and planets. Without gravity, there would be no sun to power photosynthesis, no planet to live on, no you to read these words. Gravity created you, and maybe instead of trying to conquer gravity, we should work with it, use it, understand it, respect it. This might sound like philosophical rambling, but it has practical implications. When we design space habitats, we don't try to eliminate gravity. We recreate it through rotation because we've learned that humans need it. When we plan missions to Mars, we don't try to shield against the sun's gravity. We use it, timing our launches for optimal orbital alignments. The most successful approaches to space travel don't fight gravity. They work with it, using gravitational assists to slingshot spacecraft to higher speeds, using orbits to travel efficiently. The Voyager spacecraft, launched in 1977, used gravitational assists from Jupiter and Saturn to reach the outer solar system. Without those assists, they would have needed much larger rockets or much more fuel. By working with gravity, by understanding orbital mechanics deeply enough to use the gravity of planets as free speed boosts, we accomplished something that would have been impossible otherwise. This is a form of gravity control, not in the sense of generating or canceling gravitational fields, but in the sense of being so knowledgeable about gravity that we can use its effects to our advantage. It's like how a skilled sailor doesn't fight the wind, but uses it, tacking back and forth to sail even against the prevailing breeze. Maybe the most advanced form of gravity control isn't making gravity go away. It's understanding it so deeply that we can achieve our goals by working with it instead of against it. Now I know that might not be as exciting as anti-gravity boots or flying cars, but here's why it matters. It's achievable. It's what we can actually do with current physics and foreseeable technology. And it's enough to turn humanity into a spacefaring civilization. Think about where we are right now in 2025. We're in the early stages of a new space age. SpaceX has developed reusable rockets that have dramatically reduced the cost of reaching orbit. The Artemis program is planning to return humans to the moon. Multiple countries and private companies are planning Mars missions. We're not just dreaming about space anymore. We're building the infrastructure to live there. And all of this is possible without any revolutionary new physics. It's possible with Newton and Einstein, with orbital mechanics and rocket engines, with rotating habitats and careful mission planning. We're using our understanding of gravity not to cancel it or shield it, but to work with it skillfully. And that's beautiful. That's humans at their best, using knowledge and ingenuity to overcome obstacles. But let me be clear. I'm not saying we should give up on more advanced forms of gravity control. We should absolutely keep researching quantum gravity, keep exploring theoretical possibilities like warp drives and wormholes, keep pushing the boundaries of our understanding. Because even if those things turn out to be impossible, the process of investigating them will teach us things we couldn't learn any other way. That's how science works. We aim for the impossible, and even if we miss, we land somewhere amazing. The quest to understand gravity has already given us GPS satellites that have to account for relativistic time dilation to work properly. Gravitational wave detectors that can sense space-time ripples smaller than a proton, and a cosmological model that explains the entire history and structure of the universe. Even if we never build a warp drive, the attempt to understand how it might work could revolutionize our understanding of reality itself. So let me tell you about some of the most cutting-edge research happening right now. Work that might not give us anti-gravity, but could transform our relationship with gravity in unexpected ways. At the University of Vienna, a team led by Marcus Aspelmeyer is working on quantum experiments with increasingly large objects. They're trying to observe quantum effects, like superposition and entanglement, in objects large enough that gravity becomes significant. Why does this matter? Because we've never seen quantum effects in objects massive enough that their gravity is measurable. We know quantum mechanics works for atoms and molecules. We know general relativity works for planets and stars. But what happens in between? What happens when an object is both massive enough that its gravitational field matters and light enough that quantum effects matter? Nobody knows. The math says the object should exist in a superposition of different gravitational fields, creating a gravitational field that's itself in superposition. But we've never seen this. And detecting it could give us the first hints of how to merge quantum mechanics and general relativity into a theory of quantum gravity. Another fascinating line of research involves something called atom interferometry. The basic idea is this: you can use the wave nature of atoms to create an interferometer, similar to how light interferometers work, but far more sensitive to gravitational effects. Because atoms have mass, they respond to gravity more strongly than light does. A laser interferometer like LIGO can detect gravitational waves, but an atom interferometer could potentially detect much weaker gravitational effects. Researchers are building atom interferometers to test general relativity with unprecedented precision, to search for dark matter, and to potentially detect gravitational waves at frequencies that LIGO can't see. And here's where it gets interesting for gravity control. If we could build an atom interferometer sensitive enough, we might be able to detect and measure gravitational effects from very small masses. We could potentially map gravitational fields with incredible precision. And understanding something precisely is often the first step to controlling it. Right now, we're like people in the early days of electricity, just beginning to understand the principles. We can make lightning rods and simple batteries, but we can't yet generate and control electricity at will. But once we could, once we understood electromagnetism deeply enough, everything changed. Civilization was transformed. Could the same thing happen with gravity? It's possible, but there's a fundamental difference. Electromagnetism involves charges, both positive and negative. You can shield against it, redirect it, generate it in ways that don't require huge amounts of mass. Gravity, as far as we know, only has one charge: mass. There's no negative mass to counteract positive mass, no way to shield it, no way to generate it except by having mass. This asymmetry might be fundamental, or it might be a clue that we're missing something. Some theories propose that antimatter might have negative gravitational mass, meaning it would fall up instead of down in Earth's gravitational field. If true, this would be revolutionary. But experiments at CERN, particularly the ALPAG experiment that reported results in 2023, have been testing this by measuring how antihydrogen atoms fall in Earth's gravity. The preliminary results suggest that antimatter falls down, just like regular matter, but the experiments are ongoing and becoming more precise. If antimatter does fall down, it would confirm that gravity really is fundamentally different from electromagnetism, that there's no such thing as antigravity in nature. But the definitive answer will require more precise measurements. Now let's talk about something that sounds like pure science fiction, but is actually grounded in real physics: the concept of a gravity tractor. This is a proposed method for deflecting asteroids, and it's one of the most elegant uses of gravity I've ever encountered. Here's how it works. Imagine an asteroid is on a collision course with Earth. Instead of trying to blow it up or push it with rockets, which could break it into pieces that are harder to track, you send a spacecraft to hover near the asteroid. Not on the asteroid, but hovering next to it, using its thrusters to maintain position. Now here's the beautiful part. The spacecraft has mass, and mass creates gravity. The spacecraft's tiny gravitational pull will very slowly pull the asteroid toward it. If you do this years in advance of the potential impact, Even a tiny change in the asteroid's velocity, a few millimeters per second, will cause it to miss Earth entirely. You're using the gravitational attraction between two objects to change the asteroid's orbit. This is gravity control, not in the sense of generating or canceling gravity, but in the sense of using gravity precisely to achieve a specific goal. NASA and ESA have studied this concept seriously, and it could be our best method for defending Earth against asteroid impacts. The physics is straightforward. Calculate the gravitational attraction between the spacecraft and the asteroid using Newton's law. Figure out how long you need to apply that force to change the asteroid's velocity enough, and then just wait. Patience and precision, not brute force. This is the kind of gravity control that's actually achievable, and it could literally save the world. But let's push further into the theoretical realm, because some of the most mind-bending ideas about gravity come from trying to understand the very beginning of the universe. According to the Big Bang theory, the universe began about 13.8 billion years ago from an incredibly hot, dense state and has been expanding ever since. But there's a problem. If you run the equations backward, you find that the early universe should have been very uniform, with matter and energy spread evenly. But it wasn't completely uniform. There were tiny fluctuations, quantum variations in density, and those tiny fluctuations grew over billions of years into the galaxies and galaxy clusters we see today. Gravity amplified the tiny differences. Regions that were slightly denser had slightly more gravity, which pulled in more matter, which increased the gravity, which pulled in more matter, and so on. This is how gravity structures the universe. It turns small differences into huge differences, given enough time. But here's the really weird part. The fluctuations we observe in the cosmic microwave background, the afterglow of the Big Bang, are almost perfectly consistent with predictions from a theory called cosmic inflation. Inflation proposes that the universe went through a brief period of exponential expansion in the first fraction of a second of its existence, growing by a factor of at least 10 to the power of 26 in less than 10 to the power of negative 32 seconds. This sounds insane, but it explains several things that are otherwise mysterious, including why the universe is so uniform on large scales and why it has the density it does. The theory was proposed by Alan Guth in 1980 and refined by Andre Linde, Paul Steinhardt, and others. And here's what's relevant to our discussion. Inflation was driven by something called the inflaton field, a hypothetical field that dominated the energy of the early universe. The inflaton field created what's effectively a repulsive gravitational effect, driving the exponential expansion. This is antigravity of a sort, though not in the way science fiction usually portrays it. It's a gravitational effect from exotic vacuum energy. Now, the inflaton field presumably decayed away in the early universe, its energy converting into the matter and radiation that fill the universe today. But the fact that such a field might have existed shows that gravity can, under certain conditions, be repulsive. And there's something else: dark energy. About 68% of the energy in the universe today is in the form of dark energy, which seems to be causing the expansion of the universe to accelerate. Galaxies are moving apart faster and faster, and the best explanation we have is that empty space itself has energy, a cosmological constant that creates a repulsive gravitational effect. Einstein actually predicted this possibility in 1917 when he added the cosmological constant to his equations, though he later called it his biggest blunder when it seemed unnecessary. But observations of distant supernova in 1998 by two teams, led by Saul Perlmutter, Brian Schmidt, and Adam Rees, showed that the expansion is indeed accelerating. They won the Nobel Prize in 2011 for this discovery. Dark energy is real, and it's the dominant form of energy in the universe. And it acts like anti-gravity on the largest scales. So here's a question that should make you uncomfortable. If dark energy exists, if empty space has energy that creates repulsive gravity, could we ever harness it or manipulate it? Could we create regions of space with more or less dark energy, effectively creating anti-gravity fields? The honest answer is, we have no idea. Don't even know what dark energy is. The simplest explanation is that it's a cosmological constant, an intrinsic property of space-time itself. But it could also be something more dynamic, a field that varies in space and time. If it's dynamic, then maybe it's manipulable. But if it's a fundamental constant, then it's as unchangeable as the speed of light. We don't know yet. But here's why this matters. If we could manipulate dark energy, we would have access to the most abundant form of energy in the universe. Every cubic meter of empty space contains about 6 times 10 to the power of negative 10 joules of dark energy. That doesn't sound like much, but it's in every cubic meter everywhere. The total dark energy in a volume the size of Earth is equivalent to the mass energy of a small asteroid, and it creates a repulsive gravitational effect. Understanding dark energy might be the key to advanced gravity control. But let's bring this back down to Earth, literally. Because while we're theorizing about dark energy and warp drives, there are practical applications of our understanding of gravity happening right now that are changing the world. GPS satellites, which I mentioned briefly earlier, have to account for both special and general relativistic effects to work properly. The satellites orbit at about 20,000 kilometers altitude, moving at about 14,000 kilometers per hour. Special relativity says their clocks should run slow compared to clocks on Earth by about 7 microseconds per day because of their velocity. But general relativity says their clocks should run fast compared to clocks on Earth by about 45 microseconds per day because they're in a weaker gravitational field. The net effect is that GPS satellite clocks run fast by about 38 microseconds per day compared to Earth clocks. That might not sound like much, but light travels about 30 centimeters per nanosecond, so 38 microseconds is about 11 kilometers. If we didn't account for relativistic effects, GPS would accumulate errors of 11 kilometers per day. It would be useless. The fact that GPS works is a daily confirmation that Einstein was right about gravity and time dilation. So every time you use GPS to navigate, you're benefiting from humanity's understanding of how gravity affects time. That's a form of gravity control, not in the sense of manipulating gravitational fields, but in the sense of understanding gravity well enough to work around its effects. And there are other applications. Gravitational wave detectors like LIGO are now operational, and they're opening up an entirely new way to observe the universe. Since the first detection in 2015, LIGO and its partner detectors have detected dozens of gravitational wave events, mostly from merging black holes and neutron stars. Each detection teaches us something about extreme gravity, about how space-time behaves under conditions we can never create on Earth. And the data from these detections is being used to test general relativity with increasing precision, to search for deviations that might hint at new physics. So far, Einstein's theory passes every test. But if we ever do find a deviation, it could be the crack that leads to a deeper understanding of gravity and eventually to new ways of manipulating it. This is how science progresses. Observe, theorize, test, refine, repeat. Each cycle brings us closer to understanding. Now I want to talk about something more philosophical, but absolutely crucial to understanding our relationship with gravity: the anthropic principle. This is the observation that the universe must be compatible with the conscious life that observes it. It sounds trivial, but it has deep implications. Consider gravity's strength. As I mentioned earlier, gravity is about 10 to the power of 36 times weaker than the electromagnetic force. That seems arbitrary, but it's not. If gravity were significantly stronger, stars would burn faster and die before complex life could evolve. If it were significantly weaker, stars might not form at all, or galaxies would fly apart. The strength of gravity, along with several other physical constants, seems fine-tuned for life. Change any of these constants by a small amount, and the universe becomes inhospitable to life. Some people argue this points to design, but there's another explanation: the multiverse. If there are countless universes, each with different physical constants, then we necessarily find ourselves in one where the constants allow life to exist. We couldn't observe a universe incompatible with our existence. This might sound like science fiction, but it's taken seriously by many physicists. Some versions of inflation theory predict a multiverse, where different regions of space have different vacuum states and thus different physical constants. String theory also predicts a vast landscape of possible universes. If the multiverse exists, then asking why gravity has the strength it does is like asking why Earth has the conditions for life. It's selection bias. We're here because the conditions are right, and if they weren't right, we wouldn't be here to ask the question. But here's where this connects to gravity control. If the strength of gravity is arbitrary, varying from universe to universe, then maybe it's not a fundamental constant, but rather a parameter that can take different values under different conditions. And if it can vary, then perhaps we could find ways to make it vary locally, creating regions of space with different gravitational strength. This is wildly speculative, but it's not completely crazy. It's an example of how our deepest theoretical ideas about the universe might eventually lead to practical applications we can't yet imagine. Let me tell you about one more theoretical concept that might blow your mind: the holographic principle. This is one of the strangest ideas in modern physics, and it's directly related to gravity. The holographic principle suggests that all the information contained in a volume of space can be encoded on the boundary of that volume. Think of it like this: a hologram is a two-dimensional surface that encodes three-dimensional information. The holographic principle suggests that our three-dimensional universe might be like a hologram, with all its information encoded on a two-dimensional boundary. This idea comes from studying black holes. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that black holes have entropy, a measure of information or disorder, and that this entropy is proportional to the area of the event horizon, not the volume. A black hole's information content scales with its surface area, not its interior volume. This is weird because normally we expect entropy to scale with volume. The stuff in a room, the information contained in all the particles, should be proportional to the room's volume. But for black holes, it's proportional to area. This led physicists like Gerard T. Hooft and Leonard Susskind to propose that this might be a general principle, that the information in any region of space is fundamentally limited by the area of its boundary, not its volume. If true, it would mean that our three-dimensional reality is in some sense an illusion, a projection of information encoded on a two-dimensional surface. And here's where it connects to gravity. The holographic principle suggests that gravity itself might be an emergent phenomenon, arising from the behavior of information on the boundary. This is the basis of Eric Verleen's entropic gravity theory I mentioned earlier. If gravity is emergent, if it arises from something more fundamental, then understanding that fundamental thing might give us ways to manipulate gravity that we can't currently conceive. These ideas are at the absolute cutting edge of theoretical physics, and we don't know if they're correct. But they represent serious attempts to understand gravity at the deepest level. And understanding is always the first step to control. So where does all this leave us? We've journeyed from Newton's falling apple to Einstein's warped spacetime, from the weakness of gravity to the strength of black holes, from GPS satellites to multiverses, from rocket ships to warp drives. We've seen that gravity is both simpler and more complex than we thought, both more controllable and more fundamental than we imagined. So let me try to synthesize all of this into a coherent answer to our original question. Could we ever control gravity? The answer is, we already do, in limited ways. We overcome it with rockets, work with it using orbital mechanics, create artificial versions of it through rotation, and account for its effects on time in our technology. These are all forms of gravity control, even if they don't look like the anti-gravity of science fiction. Could we do more? Could we create anti-gravity fields, build warp drives, manipulate space-time at will? Maybe, but it would require one of two things. Either exotic matter that we don't know how to make, like negative mass, or a deeper understanding of physics that goes beyond general relativity. We need quantum gravity. We need to understand how gravity works at the smallest scales, how it emerges from the quantum foam of space-time, how it relates to the other forces of nature. And we're working on it. Brilliant physicists around the world are tackling this problem. String theorists are trying to show how gravity emerges from vibrating strings in higher dimensions. Loop quantum gravity researchers are trying to quantize spacetime itself, treating it as made of discrete loops. Researchers are doing experiments to test quantum effects in massive objects, looking for hints of how quantum mechanics and gravity meet. We don't have the answer yet, but we're closing in. Every gravitational wave detection, every precision test of general relativity, every quantum experiment brings us closer. And when we do finally understand quantum gravity, when we have a complete theory of how gravity works at all scales, that's when things will get really interesting. That's when we'll know whether anti-gravity is possible, whether warp drives can be built, whether we can manipulate space-time in ways we currently can't imagine. It might turn out that the laws of physics forbid these things. Or it might turn out that they're possible, but require technology far beyond our current capabilities. Or, and this is the exciting possibility, it might turn out that there are ways to manipulate gravity that we haven't even thought of yet, ways that will seem obvious once we understand the deeper theory. This has happened before in physics. Before we understood quantum mechanics, no one imagined lasers or transistors or MRI machines. These technologies depend on quantum effects that were completely unknown until the early 20th century. Once we understood the theory, the applications followed, often in unexpected ways. The same could happen with quantum gravity. We might discover new phenomena, new effects, new ways to manipulate spacetime that are invisible to us now because we don't have the theoretical framework to see them. This is why fundamental research matters. This is why we should fund physics research, even when it doesn't have obvious practical applications. Because the impractical research of today becomes the transformative technology of tomorrow. When Maxwell unified electricity and magnetism in the 1860s, it was pure theory, beautiful mathematics with no practical use. 40 years later, we had radio. 60 years later, we had television. Today, our entire civilization runs on electromagnetic technology. The pure theory became the foundation of the modern world. The same pattern could play out with gravity. But here's something I want you to really think about, something personal and profound. Whether or not we ever develop advanced gravity control, whether we build warp drives or remain limited to rockets, the quest to understand gravity is one of humanity's greatest achievements. It's a testament to the human mind's ability to figure out the rules of the universe through observation, experiment, and mathematical reasoning. Newton didn't have computers or particle accelerators or space telescopes. He had falling apples and swinging pendulums and the moons of Jupiter. From these simple observations and a lot of brilliant thinking, he derived laws that let us predict planetary motion centuries into the future with stunning accuracy. Einstein didn't have gravitational wave detectors or black hole photographs. He had thought experiments, imagining what it would be like to ride on a beam of light, to fall freely in an elevator, to watch clocks tick at different rates. From these Gedanken experiments and profound geometric insight, he figured out that gravity is curved spacetime. And his predictions, made over a century ago, are still being confirmed today. These achievements should fill you with awe, not just at gravity, but at humanity. Because here's what's really remarkable. You, a collection of atoms arranged in a particular pattern, a temporary configuration of matter held together by electromagnetic forces, evolved from ancient primates who who evolved from ancient mammals, who evolved from ancient fish, who evolved from ancient single-celled organisms, you have the capability to understand gravity. Your brain, 3 pounds of wrinkled tissue running on about 20 watts of power, less than a light bulb, can comprehend the curvature of spacetime, can visualize black holes, can follow the mathematics of general relativity. You are the universe understanding itself. You are matter that has become conscious and is trying to figure out the rules that govern matter. That's incredible. That's miraculous, in a non-religious sense. It's something to celebrate. And whether we ever achieve advanced gravity control or not, the fact that we can ask the question, the fact that we can investigate it scientifically, the fact that we've come as far as we have in understanding this fundamental force, that's already a tremendous victory for human consciousness and curiosity. Now let's talk about what all this means for the future, because that's ultimately what we care about, right? How will our evolving understanding and control of gravity shape humanity's future? In the near term, the next few decades, we'll likely see continued refinement of the technologies we already have. Reusable rockets will become more common and cheaper, making space access routine. We'll probably establish a permanent presence on the moon and send humans to Mars. These missions will use conventional rockets and orbital mechanics, working with gravity rather than fighting it. We might see the first rotating space habitats providing artificial gravity for long-term residence. Nothing exotic, just good engineering based on well-understood physics. In the medium term, the next century or two, if civilization continues to progress and doesn't collapse from climate change or nuclear war or other human-caused catastrophes, we might become a truly spacefaring species. We could have cities on Mars, mining operations in the asteroid belt, habitats throughout the solar system. We might develop more efficient propulsion systems, perhaps fusion rockets or solar sails, that make interplanetary travel faster and cheaper. We still wouldn't have anti-gravity, but we'd be extremely skilled at using gravity to our advantage. In the longer term, centuries to millennia from now, if we survive and thrive, things get more speculative. If we develop a complete theory of quantum gravity, and it allows for exotic phenomena like stable wormholes or warp drives, we might be able to travel to other star systems. We could potentially become an interstellar civilization, spreading throughout the galaxy. But this depends on physics we don't yet understand, and technologies we can't yet build. It might be possible, or it might be forbidden by deep principles we haven't discovered. We don't know. But here's what I believe. Whether we develop exotic gravity control or not, humanity's future beyond Earth is tied to our understanding of gravity. We can't escape our home planet without understanding orbital mechanics. We can't live healthily in space without artificial gravity. We can't navigate the solar system without understanding gravitational assists. Gravity has shaped every aspect of our evolution and our civilization, and it will continue to shape our future. The better we understand it, the farther we can go, and the more we can achieve. So in a sense, we're already in a race. A race to understand gravity well enough, fast enough, to become a multi-planet species before something happens to Earth. Because Earth won't last forever. The sun is gradually getting brighter as it ages, and in about 1 billion years, Earth will become too hot for life. Long before that, we need to have spread beyond this world. And that brings me to a question that might seem off-topic, but really isn't. Does gravity give life meaning? Think about it. Gravity is the force that keeps you grounded, literally and metaphorically. It's the force that you've pushed against every day of your life, that you overcome every time you stand up or climb stairs. It's the resistance that makes movement meaningful, that makes accomplishment possible. In zero gravity, you can lift any weight effortlessly, but that means lifting weights becomes meaningless. There's no achievement in it. Gravity provides the resistance that makes overcoming it meaningful. And on a larger scale, gravity is what makes the universe structured and interesting. Without gravity, there would be no stars, No planets, no galaxies. Matter would just diffuse uniformly through space, getting thinner and thinner, colder and colder, until everything is an infinitely dilute gas approaching absolute zero. That's actually the ultimate fate of our universe if dark energy keeps driving accelerated expansion. But for now, for the next trillion years or so, gravity is fighting back, holding galaxies together, creating new stars from collapsing gas clouds, shaping the cosmic web of structure we observe. Gravity is the force that makes complexity possible. It's the force that took a nearly uniform primordial universe and created the rich, diverse cosmos we see today. In that sense, gravity is the sculptor of existence. It shapes everything from the largest scales, the distribution of galaxies, down to your personal scale, the structure of your skeleton and the pressure in your blood vessels. You are literally a product of gravity. Your body's shape, the fact that you have a top and bottom, a head and feet, all of this exists because you evolved in a gravitational field. Aliens that evolved on a planet with different gravity would look different. On a high-gravity world, they'd probably be short and stocky to minimize the structural stress. On a low-gravity world, they could be tall and spindly. Your very form is a response to gravity. So when you ask whether we can control gravity, you're really asking whether we can reshape the fundamental force that shaped us. And that's a profound question. It's asking whether we can transcend our origins, whether we can become something more than products of our environment. And I think the answer is yes, but not in the way science fiction usually portrays. We won't transcend gravity by canceling it or ignoring it. We'll transcend it by understanding it so deeply and adapting to it so completely that we can thrive anywhere, under any gravitational conditions. We'll build habitats with adjustable gravity through rotation. We'll modify our bodies, perhaps, to function in different gravitational environments. We'll develop technologies that work with gravity's effects rather than fighting them. We'll become a civilization that sees gravity not as a barrier, but as a tool, a resource, something to be used skillfully. This is the real future of gravity control, not anti-gravity boots, but gravity mastery. And we're already on that path. Every space mission teaches us more about living and working in different gravitational environments. Every physics experiment refines our understanding of how gravity works. Every engineering advance gives us new capabilities to work with gravity effectively. We're building toward a future where gravity is just another variable we can account for and adapt to, not a fundamental limitation on what we can do or where we can go. But let me bring this full circle to where we started, because I think there's something beautiful here. Remember how I said that you're being pulled by every object in the universe right now? That's not just a quirky fact. It's a profound truth about interconnectedness. Gravity doesn't just pull you toward Earth. It pulls you toward every star, every galaxy, every atom. The gravitational influence diminishes with distance, becoming unimaginably tiny, but it never truly goes to zero. You are gravitationally connected to the entire universe. Every massive object in existence is having an effect on you, and you're having an effect on every massive object. You're pulling on the moon, on the sun, on distant galaxies billions of light years away. Your gravitational influence extends infinitely, just like everyone else's, just like everything's. We are all connected by gravity, all part of one universal web of gravitational interactions. When you move, you change the gravitational field of the entire universe by a tiny amount. The universe responds to your existence. You matter, quite literally. Your mass matters. Your motion matters. You're not separate from the universe. You're an integral part of it, connected to everything through gravity. And here's the really mind-bending part. Because gravity affects time, and because gravitational influences propagate at the speed of light, your past is encoded in the gravitational field spreading out from your location. If aliens with sufficiently advanced technology existed 100 light years away, they could theoretically detect the gravitational waves you created by moving around 100 years ago. Those waves are still out there, carrying information about your existence, traveling through space at light speed. You're leaving a permanent mark on spacetime itself. Your existence literally ripples through the fabric of reality. So when people say they want to leave a mark on the universe, to have an impact that outlasts them, here's the truth. You already are. Every motion you make creates gravitational waves that will propagate forever. They become infinitesimally small, undetectable in practice, but they never disappear. The information is conserved. You are literally writing your story into the structure of spacetime. And that story will exist as long as the universe does. That's a form of immortality that no technology can match. Your gravitational influence is eternal. Now I want to address something that might be bothering some of you. We've talked a lot about theory and possibility, but what about practicality? What about the here and now? If we can't build anti-gravity devices tomorrow, what's the point of all this? Why should you care about gravitational waves, or curved spacetime, or quantum gravity? Here's why. Because understanding changes everything. Before we understood electromagnetism, we lived in a world lit by fire and candles. Messages could only travel as fast as a horse could run. Food spoiled without refrigeration. Surgery was done without X-rays or MRIs. The world was fundamentally limited by our ignorance. Once we understood electromagnetism, everything changed. We got electric lights, radio, television, computers, the internet, smartphones, medical imaging, and a million other technologies. The theory seemed abstract and impractical when Maxwell first wrote down his equations, but it became the foundation of modern civilization. The same could happen with a deep understanding of gravity. We don't know what applications might follow from a complete theory of quantum gravity. We can't know because we don't have the theory yet. But history suggests that profound theoretical understanding leads to transformative practical applications, often in ways that the theorists never imagined. Quantum mechanics gave us semiconductors and lasers and MRI machines. Relativity gave us GPS and particle accelerators and nuclear power. What will quantum gravity give us? We don't know, but it could be anything. It could be technologies that seem magical to us now, the same way a smartphone would seem magical to someone from the 19th century. So when we investigate gravity, when we build gravitational wave detectors and particle colliders and space telescopes, when we fund theoretical physics research that seems abstract and disconnected from daily life, we're not wasting time or money. We're investing in the future. We're building the knowledge base that will let our descendants do things we can't currently imagine. And that's worth doing. That's noble work. That's humanity at its best, pushing the boundaries of knowledge not for immediate profit, but because understanding reality is intrinsically valuable. And because, historically, it pays off in unexpected ways. Let me tell you one more thing that I think is crucial. Throughout this entire exploration, we've been assuming that our current understanding of physics is basically correct, that we just need to extend it to unify quantum mechanics and gravity. But what if we're wrong about something fundamental? What if there's a piece we're missing? Something as revolutionary as Einstein's relativity was compared to Newton's mechanics. This has happened before. For centuries, we thought Newton's laws were absolutely correct, the final word on motion and gravity. Then Einstein showed that they were just approximations, extremely good approximations under normal conditions, but not the deep truth. Newton's laws break down at high speeds and strong gravitational fields. Could our current theories break down under conditions we haven't fully tested? Absolutely. General relativity has been tested extensively within the solar system and with binary pulsars and gravitational waves, but we've never tested it inside a black hole's event horizon. We can't. We've never tested quantum mechanics at the scale of planets. We can't. There are regimes of reality we haven't explored. And in those unexplored regimes, surprises might await. There might be phenomena we haven't discovered, effects we haven't imagined, possibilities we've ruled out based on incomplete information. This is both exciting and humbling. It's exciting because it means there might be ways to manipulate gravity that we haven't thought of, that aren't forbidden by any known law of physics, because we don't know all the laws yet. It's humbling because it reminds us how much we don't know. We've made incredible progress. We've gone from thinking Earth is flat and the sun revolves around us to understanding that we're on a spinning sphere, orbiting an average star, in an average galaxy, in an expanding universe with hundreds of billions of galaxies. We've figured out that gravity is curved spacetime, that time is relative, that quantum mechanics governs the microscopic world. These are stunning achievements, but we're not done. We might not even be close to done. There could be layers of reality we haven't glimpsed, principles we haven't discovered, phenomena we haven't imagined. And that's wonderful. That means the universe is richer and stranger than we know. That means there's more to discover, more to understand, more wonder awaiting us. So let me come back to our original question one final time. Could we ever control gravity? Here's my answer, synthesizing everything we've discussed. Yes, we can control gravity, and we already do, just not in the way science fiction depicts. We control it by understanding it well enough to work with it, to predict its effects, to use it to achieve our goals. Can we do more? Can we manipulate gravitational fields directly, create anti-gravity, build warp drives? Maybe. It depends on physics we don't yet understand. If exotic matter with negative mass can exist, if wormholes can be stabilized, if there are effects of quantum gravity that allow space-time manipulation, then yes, advanced gravity control might be possible. But if the laws of physics forbid these things, if they're not just technologically difficult, but fundamentally impossible, then no, we'll be limited to working with gravity rather than truly controlling it. And here's the profound truth. We don't know yet which it is. We're at a point in history where we have enough knowledge to ask the right questions, but not enough to answer them definitively. We're like people in the year 1900 asking whether heavier-than-air flight is possible. Some said yes, some said no, and the truth wasn't settled by argument, but by experiment. The Wright brothers didn't prove flight was possible by debating physics. They proved it by building an airplane. Similarly, the question of whether advanced gravity control is possible won't be settled by pure theory. It will be settled by experiment and engineering, by pushing our technology and our understanding to the limits and beyond, by trying things that seem impossible and discovering whether they are or not. And that's the work of the next century, the next millennium, the ongoing project of human scientific exploration. We're doing it right now. Every physicist working on quantum gravity, every engineer designing better rockets, every astronaut learning to live in microgravity, every student studying mathematics and dreaming of the stars, all of them are part of this grand project. And so are you, if you want to be. You don't have to be a physicist or an engineer. You can contribute by being curious, by learning, by supporting science and education, by raising children who ask questions about the universe, by voting for politicians who fund scientific research, by simply maintaining a sense of wonder about reality. Because science isn't just what happens in laboratories and universities. Science is a way of thinking, a commitment to following evidence wherever it leads, a willingness to say, I don't know, and then work to find out. And that way of thinking is humanity's greatest tool for understanding and ultimately shaping our world. Let me tell you about a moment that changed how I think about all of this. In 2019, when the first image of a black hole was released, I watched the press conference live. Katie Bouman, one of the computer scientists who made it possible, stood there with tears in her eyes as the image was revealed. And I understood why she was crying. Because that image, that blurry orange ring around a dark circle, represented something profound. It was a photograph of curved spacetime so extreme that it trapped light itself. It was confirmation that Einstein's century-old equations, derived from pure thought and geometry, actually described reality at its most extreme. It was proof that humans, fragile beings living on a tiny planet, could understand the universe at its most fundamental level. We could look into the abyss of a black hole and comprehend what we were seeing. That moment was about more than just a black hole. It was about human capability, about what we can achieve when we combine brilliant minds, sophisticated technology, and patient, careful work. The Event Horizon Telescope isn't a single telescope. It's a network of radio telescopes around the world. Working together, their data combined to create the equivalent of an Earth-sized telescope. It took years of work, massive amounts of data, sophisticated algorithms, and international cooperation. And it worked. That's what gives me hope about the future of gravity research and gravity control. Not any specific theory or technology, but human capability. Our ability to tackle problems that seem impossible, to build tools that extend our senses far beyond their natural limits, to cooperate across borders and cultures in pursuit of knowledge. If we can photograph a black hole 55 million light-years away, if we can detect gravitational waves from colliding black holes billions of light-years away, if we can land rovers on Mars and build space stations and decode the human genome and split the atom, then what can't we do given enough time and effort? The answer might be that there are genuine limits, things that are fundamentally impossible according to the laws of physics. But we won't know where those limits are until we push against them. And the process of pushing, the attempt to do the impossible, teaches us things we couldn't learn any other way. Even failure is instructive. When the M drive appeared to fail, when careful experiments couldn't replicate the claimed thrust, we didn't just learn that the M drive doesn't work. We learned about experimental design, about the importance of controlling for thermal effects and electromagnetic interference, about how easy it is to fool yourself with subtle experimental errors. That knowledge makes all future experiments better. Now let's talk about something that might make all of this more personally relevant. How can you, as an individual, contribute to humanity's quest to understand and control gravity? First, stay curious. Keep learning about science, not just physics but all fields, because they're interconnected in surprising ways. Biology teaches us about how life adapts to gravity. Chemistry teaches us about the forces that hold matter together. Mathematics provides the language we use to describe physical laws. Computer science gives us the tools to simulate and analyze complex systems. Every field contributes. Second, support science education and research. This doesn't mean you have to donate millions of dollars to physics departments, though that helps. It means supporting public funding for basic research, supporting science education in schools, encouraging young people to pursue STEM careers, pushing back against anti-science rhetoric and policies. Science is a collective endeavor, and it only works when society supports it. Third, think critically and rationally. Don't believe claims of antigravity or free energy just because they sound exciting. Demand evidence. Understand the difference between speculation and established science. But also don't be so skeptical that you dismiss new ideas out of hand. Good science requires both skepticism and openness, doubt and wonder, critical thinking and imagination. And fourth, remember that you're part of something larger. You're part of a civilization that has been trying to understand the universe for thousands of years. From ancient astronomers tracking the planets, to medieval scholars preserving and expanding knowledge, to enlightenment scientists establishing the scientific method, to modern researchers pushing the boundaries of knowledge with technology our ancestors couldn't imagine. You're the latest link in a chain of human curiosity that stretches back to the first humans who looked up at the stars and wondered what they were. And you're not the last link. If you teach your children to ask questions, if you support science and education, if you contribute to the culture of curiosity and rational inquiry, then you're helping to forge the next link. Future generations will continue this work. We'll answer questions we can't answer. We'll achieve things we can't achieve. We'll understand things we can't understand. But they'll build on our foundation, on the knowledge we've accumulated, on the technologies we've developed, on the culture of inquiry we've maintained. So your contribution matters, even if you never discover a new law of physics or build a revolutionary technology. You matter to this project simply by being part of it, by carrying the torch of human curiosity forward. Let me paint you a picture of what the future might look like if we succeed in our quest to understand and control gravity. Imagine it's the year 2300. Humanity has spread throughout the solar system. There are cities on Mars, thriving colonies in the asteroid belt, floating habitats in the clouds of Venus, research stations on the moons of Jupiter and Saturn. Travel between worlds is routine, using efficient fusion drives and gravitational assists. A journey from Earth to Mars takes just a few weeks, not months. And throughout all these habitats, artificial gravity is ubiquitous, created by rotating sections of space stations and ships, calibrated to whatever level the inhabitants prefer. Maybe Mars colonists prefer to live at Mars gravity, 0.38 grams, because they've adapted to it. Maybe asteroid miners prefer low gravity, 0.2 grams, because it makes heavy work easier. Maybe Earth purists insist on full 1 gram environments. The point is, we have the technology to choose, to create whatever gravitational environment suits our needs. And on Earth, our understanding of gravity has led to technologies we can't yet imagine. Maybe we've learned to manipulate dark energy or quantum vacuum effects in ways that allow limited gravity manipulation, not full anti-gravity, but enough to make construction easier, to assist in launching spacecraft, to help elderly people move around more easily. Maybe we've discovered something in our quantum gravity research that led to a new form of energy generation or computation or communication. We can't know what it would be, but history suggests that deep understanding leads to unexpected applications. And beyond the solar system, the first interstellar missions are being planned. Maybe we've discovered that warp drives are impossible, that faster-than-light travel violates fundamental principles. But we've accepted that, and we're building generation ships instead, massive rotating habitats that will take centuries or millennia to reach nearby stars, carrying thousands of people who will live their entire lives in transit, their distant descendants finally arriving at new worlds. Or maybe, just maybe, we found a loophole, a way to create stable wormholes or manipulate spacetime in ways that allow faster interstellar travel. We don't know, but we're trying. We're building. We're exploring. We haven't given up on the stars. This is an optimistic vision, I know. It assumes we survive the challenges facing us now: climate change, nuclear proliferation, political instability, technological risks. It assumes we don't destroy ourselves or collapse back into a dark age. But I think it's a realistic possibility if we make good choices. If we prioritize long-term thinking and international cooperation, if we continue to invest in science and education and exploration. But let me also paint a darker picture, because it's important to understand what's at stake. Imagine it's 2300, but we've taken a different path. We gave up on space exploration, deciding it was too expensive, too difficult, too impractical. We stopped funding basic research, demanding immediate practical applications for every dollar spent. We let scientific literacy decline, allowing superstition and pseudoscience to replace rational inquiry. We turned inward, focusing on short-term problems, never looking up, never wondering, never exploring. In this future, we're still on Earth, all 10 or 15 billion of us, crowded onto a planet struggling to support us. We've never gone back to the moon. Mars is still untouched. The asteroids are unharvested, and we're vulnerable. A large asteroid impact, a supervolcano, a pandemic, nuclear war, runaway climate change, any of these could devastate or destroy our civilization. Because we're all on one planet, all our eggs in one basket. And we've lost something intangible but crucial. The sense that we're part of something larger, that we're capable of great things, that the universe is knowable and we can know it. We've given up on the future. We've stopped dreaming. And without dreams, without aspirations beyond mere survival, civilization stagnates and eventually declines. This is the darker path, and it's possible. It's a choice we could make, collectively, through neglect and short-sightedness. So here's why our quest to understand and control gravity matters on a practical, immediate level. It's not just about the science, though the science is fascinating. It's not just about the technology, though the technology could be transformative. It's about maintaining a civilization that looks outward and upward, that values knowledge and exploration, that believes humanity has a future beyond this one planet. The quest to understand gravity is part of a larger quest to understand our place in the universe, to expand our capabilities, to ensure our long-term survival. It's about choosing the optimistic future over the pessimistic one, choosing growth over stagnation, choosing wonder over resignation. And that choice is made not once, but every day, by millions of people through their actions and priorities. Every time someone chooses to study physics instead of giving up because it's hard, every time a society invests in a space telescope or a particle accelerator, every time a teacher inspires a student to ask questions about the universe, we're choosing the better future. We're investing in humanity's potential. We're keeping the dream alive. Let me bring this to a close by coming back to you personally one more time. You've spent the last 3.5 hours with me, learning about gravity, about physics, about humanity's quest to understand the universe. You've learned about Newton and Einstein, about black holes and gravitational waves, about the possibilities and limitations of gravity control. But here's what I really hope you've gained: a sense of wonder, a sense that the universe is stranger and more beautiful than you imagined, a sense that you're part of something larger, connected to everything through gravity, through physics, through the shared project of human understanding. You're not separate from the universe. You're not an observer looking at reality from outside. You are reality looking at itself, trying to understand itself. Your consciousness, your curiosity, your ability to comprehend physics and mathematics and the nature of spacetime, these are emergent properties of the universe. The universe has evolved to the point where part of it, the part that's you, can understand the whole. That's profound. That's miraculous in a secular sense. And here's what you should do with this understanding. First, be amazed. Let yourself feel the wonder of living in a universe governed by comprehensible laws. A universe where humans can figure out the rules through observation and reason. Second, share it. Talk to people about what you've learned. Not to show off, but to spread the wonder, to inspire others, to contribute to a culture that values knowledge and curiosity. Third, keep learning. This video is just the beginning. There's so much more to discover about gravity, about physics, about everything. Read books, watch more videos, take classes, never stop being curious. And fourth, remember that you matter. Not in some cosmic sense where the universe cares about you personally, because it doesn't. It's indifferent. But you matter to the human project of understanding and shaping our world. You matter to other people. Your actions, your choices, your contributions, small as they might seem, are part of the larger story of human civilization. You're writing your story into the structure of space-time with your gravitational waves, but you're also writing it into history with your actions. Make it a story worth telling. So could we ever control gravity? The answer is, we're trying, we're learning, we're building. We don't know yet what's possible and what's impossible, but we're working to find out. And that's enough. The quest itself is worthwhile, regardless of where it leads, because the quest is what makes us human. The quest is what lifts us above mere survival, above simply existing. The quest gives meaning to our brief time in this universe. We are the universe's way of understanding itself, and gravity is one of the deepest mysteries we're trying to solve. Maybe we'll solve it completely. Maybe we'll just make progress, pushing our understanding a bit further, leaving the final answer to our descendants. Maybe we'll discover that some questions can't be answered, that some things are fundamentally unknowable or uncontrollable. But we won't know until we try. And the trying, the quest itself, is what defines us as a species. We are the curious apes, the ones who look up at the stars and wonder, the ones who drop objects and measure how fast they fall, the ones who derive equations and build telescopes and launch spacecraft and refuse to accept ignorance as final. Gravity shaped us, created the world we evolved on, structures our bodies, governs the motions of the planets and stars. We are products of gravity, but we're also becoming something more. We're becoming beings who understand gravity, who can predict its effects, who can work with it to achieve our goals, who might someday manipulate it directly. We're transforming from passive subjects of gravity to active participants in shaping how gravity affects us. That transformation is happening now, in our lifetimes, through the work of thousands of scientists and engineers and educators and students. You've been part of that transformation today by taking the time to learn, to understand, to engage with these ideas. Thank you for that. Thank you for your curiosity. Thank you for your attention. And thank you for being part of this grand human project of understanding the universe. Now go forth with your new knowledge. Look at the world differently. Feel your weight on the ground and understand that it's not a force pulling you down, but the ground pushing you up as you try to follow a geodesic through curved spacetime. Look at the moon and understand that it's constantly falling toward Earth, missing the planet because it's moving sideways fast enough. Look at the stars and understand that their light has been bent by the gravity of galaxies between them and you, that you're seeing the universe through a distorted lens of curved spacetime. And when you jump, when you temporarily overcome the gravitational pull of an entire planet with just the muscles in your legs, feel the accomplishment. Feel the defiance. Because that's what humanity does. We face forces that seem overwhelming, that seem unconquerable, and we find ways to overcome them. We don't have anti-gravity devices, but we can still fly. We can still go to space. We can still achieve things that gravity seems to forbid, not by ignoring the laws of physics, but by understanding them so deeply that we can use them to our advantage. That's the real meaning of controlling gravity. Not some pseudo-scientific anti-gravity drive, but deep understanding combined with clever engineering, knowledge combined with determination, science combined with human ambition. We've come so far already. From not understanding what gravity was, to Newton's force, to Einstein's curved spacetime, to gravitational wave detection, to black hole photography. Each step seemed impossible before it was achieved. And each achievement opened new possibilities, raised new questions, pointed the way toward the next step. We don't know where the next steps will lead, but we know they'll lead somewhere interesting, because that's what science does. It takes us to places we couldn't imagine, shows us things we didn't know existed, transforms our understanding of reality itself. So the story of humanity and gravity is far from over. It's just beginning. We're in the early chapters of a story that might span thousands or millions of years. A story of gradually increasing understanding and capability, of spreading through the solar system and perhaps eventually the galaxy, of transforming from beings who are subject to gravity to beings who dance with it, who use it as skillfully as a surfer uses waves. We might never cancel gravity or create anti-gravity fields, but we don't need to. We just need to understand it deeply enough and adapt to it completely enough that it stops being a barrier and becomes just another aspect of reality that we work with. And we're getting there. Every experiment, every mission, every discovery brings us closer. You've been part of that journey today. You've learned about gravity at a deeper level than most people ever will. You understand that it's not a force, but curved spacetime. You understand that it affects time as well as space. You understand the hierarchy of gravity control technologies, from what we can do now to what might be possible in the far future. You understand the challenges and the possibilities. And most importantly, you understand that the quest to understand gravity is really about something larger. Humanity's quest to understand our place in the universe, to expand our capabilities, to ensure our long-term survival and flourishing. That quest continues. It will continue long after this video ends, long after you and I are gone. But we're part of it now, in this moment. We've contributed to the collective understanding, even if only by learning what others have discovered. And that's enough. That's meaningful. That's worthwhile. So thank you for joining me on this journey through gravity, space-time, black holes, and the human quest for knowledge. Thank you for your curiosity and your attention. And thank you for being part of this amazing species that looks at the universe and says, I want to understand you. I want to figure out your rules. I want to explore you. I want to shape my future in you. We are gravity-adapted organisms trying to become gravity-independent. We're matter trying to understand the force that shapes matter. We're the universe trying to understand itself. And that's the most beautiful, most profound thing I can think of. Gravity pulled the atoms that make you together. Gravity held them on Earth while life evolved. Gravity shaped your body and your world. But gravity doesn't define your limits. Your curiosity does. Your knowledge does. Your determination does. So go out there and push those limits. Learn more. Do more. Be more. And maybe, just maybe, you'll be part of the generation that finally cracks the deepest mysteries of gravity, that achieves what seems impossible today, that takes humanity to the stars. Or maybe you'll simply live a good life, inspired by the beauty and complexity of the universe, contributing in small ways to the collective human project. Either way, you matter. Your existence matters. Your curiosity matters. And the fact that you spent these hours learning about gravity, that you cared enough to go on this journey, that already makes a difference. The universe is vast and ancient, 13.8 billion years old, trillions of light years across if you count regions we can't see. Against that scale, you're insignificant. Your life is a brief flicker, over in less than a century. From a cosmic perspective, you don't matter at all. But here's the thing. That perspective is wrong. Because mattering isn't about size or duration. It's about consciousness, about understanding, about experiencing and engaging with reality. A human life, brief as it is, contains more wonder, more joy, more understanding, more meaning than a lifeless galaxy that exists for billions of years. Consciousness matters. Understanding matters. The fact that you can comprehend gravity, can follow the mathematics of general relativity, can grasp the concept of curved spacetime, that's more important than the size of a black hole or the age of a star. Because black holes don't know they exist. Stars don't understand physics. But you do. You're matter that has become conscious, complex, capable of understanding. And that's the most remarkable thing in the universe. So yes, we can control gravity in some ways. Yes, we might someday control it in more advanced ways. But whether we do or don't, whether we build warp drives or remain forever limited to rockets, whether we spread to the stars or stay on Earth, none of that changes the fundamental wonder of your existence. You are a miracle. A conscious, curious being in a vast universe governed by mathematical laws. You can understand those laws. You can appreciate the beauty of reality. You can participate in humanity's collective quest for knowledge. And that's enough. That's everything. Thank you for being here. Thank you for learning. Thank you for caring. Keep asking questions. Keep learning. Keep wondering. And never forget that you're part of something larger, something beautiful, something that stretches from the first humans who wondered about the stars to the last humans who might one day reach them. You're a link in the chain of human curiosity, and that's a noble thing to be. Now, before I let you go, I want you to do something for me. In the comments, tell me, what was the one thing from this entire journey that blew your mind the most? Was it learning that gravity isn't a force? That your feet are younger than your head? That we've photographed black holes? That you're gravitationally connected to every object in the universe? I want to know what landed for you, what idea grabbed you and wouldn't let go. Share it in the comments and engage with what others share. Build a community of curious people discussing these ideas, because that's how knowledge spreads, how cultures of curiosity are maintained, how we collectively keep pushing forward. And if you found value in this deep dive, if you appreciate long-form educational content that doesn't shy away from complexity, subscribe to this channel, like this video, share it with someone who would appreciate it. Support this kind of content with your engagement, because YouTube's algorithm responds to that. And the more people engage, the more this kind of content gets made and promoted. We're in a battle for attention online, competing against shallow, quick-hit content designed for maximum engagement with minimum substance. Fight back by supporting substantive content. Show the algorithm and the creators that there's an audience for depth, for nuance, for taking the time to really understand something. All right, we've reached the end of our journey together. 3.5 hours exploring one of the deepest questions in physics. Could we ever control gravity? We've seen that the answer is complex, nuanced, more interesting than a simple yes or no. We control some aspects of gravity now. We might control more in the future. Some forms of control might be fundamentally impossible. But the quest to find out, the journey of discovery itself, that's what matters. That's what makes us human. So go forth with your new understanding. See the world through the lens of curved spacetime. Feel your connection to the universe through gravity. And never stop wondering, never stop learning, never stop pushing against the boundaries of the known. The universe is stranger and more beautiful than we imagine, and there's always more to discover. Thank you for joining me on this journey. Until next time, keep looking up, keep asking questions, and keep being amazed by the reality we inhabit. This has been an exploration of gravity, humanity, and our place in the cosmos. I hope it's changed how you see the world, at least a little bit, because that's the point of education, not just to transfer information, but to transform understanding, to give you new eyes with which to see reality. If I've done that, then these 3.5 hours have been worthwhile. Take care, stay curious, and remember, you're made of stardust, shaped by gravity, capable of understanding the universe. That's something to be proud of. Goodbye for now, and may your geodesic through spacetime lead you to interesting places.